Hello again, everyone, and thank you for attending today's webinar, Accurate Synchronization of EtherCAT Systems Using Distributed Clocks. This webinar is being brought to you by Beckhoff, EtherCAT Technology Group, and Design World Magazine. We would like to thank our presenter, Joey Stubbs, for being here today. And I'm Leslie Langnaw, Managing Editor at Design World Magazine, and I'll be your moderator. Just a couple of housekeeping details before we get started. If you wish to, you can tweet about this webinar at any time. Just use hashtag DWWebinar. This webinar will be available to everyone who is attending. It will be emailed to you afterwards, and it also will be available on the designworldonline.com website. And we will have a Q&A session at the end of the presentation, and Joey will be available for that. Right now, I'd like to introduce you to Joey Stubbs. He is the North American representative of the EtherCAT Technology Group, which is one of the largest industrial field bus organizations in the world. He has a Bachelor of Science degree in Electrical Engineering from the University of South Carolina, as well as several other technical degrees. He has more than 25 years of experience in the area of industrial automation. He is also a registered professional engineer and a registered project management professional. And without further ado, I'm going to hand over the presentation to Joey.
Thank you, Leslie. As Leslie stated, my name is Joey Stubbs with the EtherCAT Technology Group, so I represent North America. And I'm trying, there we go. So during this presentation, we're going to gain a basic understanding of how distributed clocks work in the EtherCAT network. You'll hear me abbreviate those as DCs. And then, more importantly, understand how devices designed with EtherCAT distributed clocks can benefit the user in their systems. So briefly, today we'll go through what distributed clocks are defined as, the important EtherCAT functional principles that make DCs work, an overview of the DC functionality, and then really basics of how it works, how we measure empirically propagation delay in the system, how we set the reference and slave clocks, and then how we implement drift compensation in the network, and then a quick overview of how the master compensates for making sure that the data is in the network before the DCs need it. And then a few practical applications of DCs built into slave devices. So as far as the definition of distributed clocks, in the EtherCAT world, we define distributed clocks as a logical network of synchronized distributed local clocks in the slave devices in the EtherCAT field bus system. So by using distributed clocks, EtherCAT, the real-time Ethernet protocol, is able to synchronize the time in all the bus devices within a very narrow tolerance range, typically within 100 nanoseconds. So why would we even want to synchronize a network? And not every network really needs to be synchronized. It really depends on the needs of the system. So one common implementation is to gather the time values for all devices synchronously, or gather data synchronously based on a time value. So in motion control, for example, when device 1 was at position X, device 2 was at position Z, or the data at device 1 was this when device 2 was this value. And then having cyclic behavior in the slave devices with tight time tolerances. So another example having to do with motion control, having an exact delta T allows us to grab those delta positions, delta differences, and do tighter coordinated motion or speed calculations. Also, having cyclic behavior in the slave devices can let us do data acquisition at possibly high data rates. So for like condition monitoring, for instance. and also response to an external event. So instead of having to have a built-in microcontroller on the field bus that's looking for an event to happen, having a very elegant latch time, seeing events that would be missed in a classical scanning of an I/O system, for instance. An example would be getting an exact time that an alarm occurred and using that downstream to reject bad product, like in a conveyance system or some serial manufacturing environment, and rejecting that bad product with respect to like a conveyor speed without a lot of loss of good product. And then being able to set when you want to respond to something in the field. So setting a time for a new command for drives, for instance, or executing simultaneous outputs for devices separated by long distances. So maybe a textile factory or an animation or fountain display at an amusement park. So there are some functional principles in EtherCAT that allow these distributed clocks to be implemented very efficiently and elegantly. And I'll go through these in detail, so don't worry about catching it on this slide. But we do frame processing on the fly without stopping the frame. The protocol is also processed in hardware in the slave devices in a chip. Every frame goes through a fixed frame path in the network within a given topology. We have distributed clock units that allow latching of receive times in the slave ports and in the logical processing unit of the slave devices. And we have an instruction set that lends itself really well to distributing times and time offsets easily, which will become very apparent when I'm talking about how we synchronize the network initially. Then this distributed clock unit built into the EtherCAT slave controller, which has all of this functionality, and most of it's implemented in hardware. And then probably most importantly, once you have synchronization, once you have time in common on the devices, how do you interface to that externally to your field devices on the wire? And we'll go through that. So the first of these functional principles is called Ethernet on the fly. And this is a basic functional principle of EtherCAT. So as the frame is going through the network, each slave device reads or writes to, or can read or write to, the frame if it's addressed, down to a single bit without losing any overhead. So this principle is called Ethernet on the fly. So the process data is inserted and extracted as the frame goes past. And we can do multiple scan rates on the slave on the same wire. So for instance, motion control at one rate and data acquisition at another rate, and then standard inputs and outputs like push buttons at a much different rate. And we can also do asynchronous event-triggered communication. So this frame processing is done with a low-cost ASIC or FPGA or dedicated slave controller chip called an EtherCAT slave controller, ESC. And this low-cost chip is actually undercuts the cost of a microcontroller and RAM and a software stack, and has the ability to implement all of these features of distributed clocks that I'm going to discuss today. But it's up to the vendor of the device as to whether that implementation of the distributed clocks makes sense or not. And importantly, the topology of the EtherCAT network can be any topology. So it can be lines, it can be stars, trees, daisy chains, drop lines, and we can address up to 65,535 devices within one EtherCAT network. And we can do any number of physical layer changes between 100 base TX, 100 base FX, and LVDS, which is the protocol or the physical layer between devices that are connected directly together, such as I/O terminals. So within each EtherCAT slave device is the ability to have up to 4 ports. So this allows us to do all these topology changes without the need for switches or hubs or any other active routing infrastructure. So some important things to keep in mind about EtherCAT is that the EtherCAT master, the PLC or the PC, is the only device that can create a frame. All the slave devices, their EtherCAT slave controller chips, can only modify a frame that comes past. And most importantly, the frame is not actively routed to a particular node in the EtherCAT protocol. The frame, regardless of who it's addressed to or how many devices are addressed in the same frame, travels through the entire network regardless of which node is addressed within the frame. So one frame can actually service an entire EtherCAT network depending on the amount of data. If the data size exceeds 1,500 bytes in length, the master can send out multiple frames back to back as if it was one long frame, as long as it adds an inter-packet gap to keep us IEEE compliant. So for example, this network, which was made up of a master controller and then a network of slave devices, can have a frame sent out. It'll produce a frame. That frame will go through all the devices in this order. And when it reaches the end, these are drives, by the way, at the end, there's nothing connected to the out port of the second device or at the end device. So the frame will be routed back through the receive pair of wire or whatever physical layer, and then routed, or not routed, but sent down to the next set of I/O and drives, and then go through the next set of I/O. Nothing connected at the end, so once again it'll be turned around and sent through the receive pair and make its way down to the drives, and this will continue throughout the network so that the same frame will actually go through all devices in the network and wind up back at the master with all the input data. So a single frame can service all these devices at once, but regardless of whether they're addressed or not, the frame goes through the network in the same exact order every single time. And that's important for propagation delay measurement and for distributing time, as you'll see coming up. So there's also this very unique instruction in the EtherCAT command instruction list called a read multiple write action. And this will be very important for closing the loop with our drift compensation, where we'll distribute the time from our reference clock to all the other slave devices. So keep this one in mind, but I'll talk about it in detail coming up. So inside the EtherCAT slave controller chip is the distributed clock unit. This distributed clock unit has the ability to measure delta times very efficiently. It has links over to the ports of the devices, so up to the 4 ports. Most devices have 2, port 0 and port 1 for in and out. And then a set of inputs and outputs called sync and latch pins, and they can also be routed through a interrupt line to a microcontroller. So the EtherCAT master will handle several things within the EtherCAT network to allow us to use DCs effectively. Now keep in mind that you as a user don't have to handle any of this stuff yourself. This is all handled in the background more or less automatically by the EtherCAT master, as long as it supports distributed clocks and then your slave devices have distributed clocks enabled. So the first is that we have to measure the propagation delay in the system. We do that empirically because of some of the properties of the EtherCAT slave devices, which I just talked about. So we'll measure the offset times depending on the number of devices, cable lengths, and then we even allow for dynamic changes in the configuration. So we can recalculate this at any point. Then we have to get the reference clock set to the real-time clock of the master clock in the controller or the PLC. And then we have to get all the slave clocks set to the same exact time of the reference clock. And once all those clocks are set to the same time, then we have to take care of any drift compensation, since each slave clock usually has its own oscillator, its own quartz or PLL. And even though it's a tight tolerance that we specify within the EtherCAT world of 25 parts per million, it's still possible that over a long period of time that drift will occur. So we have to take care of this. So when slave devices start up, they think that it's January 1st, 2000 at midnight. They have the ability to communicate a 64-bit time value, which gives us, with a 1 nanosecond base unit, which gives us more than 500 years worth of time counting. So hopefully that gets us past any kind of future Y2K planning. But typically we can just use the lower 32 bits. This allows us to save bandwidth, and it's good enough for 4.2 seconds, which, considering that most of these systems are very cyclical, we're sending and receiving frames much more often than 4.2 seconds, so the ability to, or the risk of drifting more than 4.2 seconds is pretty small. So within our network, we need to define one of our slave devices as a reference clock. And the reason we do this is because the slave oscillators are a much better timekeeper than any PC or PLC clock can be. This also allows us to get away from having a special master card in the controller and allows us to just use a software stack as the master controller. So this reference clock will have its time distributed cyclically to all the other slave clocks by the master. And as you'll see, we can also set this according to an external IEEE 1588 source if we need to synchronize to something external. So as I mentioned, the first thing that we need to do is measure the propagation delay in the network. So the master orchestrates this, and we send out a frame, or actually we first designate which is going to be our reference clock. And in the EtherCAT network, because of that read multiple write command and the fact that we want the propagation delay to be standard or the same, we'll designate the first distributed clock enabled device in the network to be the reference clock. And all the other ones will then be slave to that clock. And we're going to measure each individual delta t between that reference clock, or calculate, sorry, that delta t between the reference clock and each slave device. So within the EtherCAT slave controller in the DC unit, the master can send out a frame, and each DC enabled device can latch in the difference in time, or actually the running time, between the frame being registered through the processing direction and then just the forwarding direction, because that's two different ports that we're communicating through. So each port has its own register which can grab the time, plus a register called system time delay. So the latch of that frame, the start of frame, occurs when the frame is received at any of these ports. And at the end of frame, after the CRC is checked, that start of frame time is copied into the register. And then the master can then grab all of those timestamps And since it knows what the topology of the network looks like, with those timestamps, it can calculate the propagation delay between the reference clock and any individual slave device, and then write those time delays into each slave device's system time delay register. And I have a graphic coming up. There we go. So the master grabs all of these delta times. It knows what the topology looks like because it knows which ports are open, closed, what devices are hanging downstream of each port, and tabulates the propagation delay between the reference clock and each slave device, and then distributes that delta time to each of the slave devices, and it'll be different for each slave device. So from the reference clock to the slave device, that time is written. Okay, so now we know what the propagation delay between the reference clock and each slave device is, but we still don't know what exact time it is in each of the slave devices, or in the reference clock for that matter. So now we have to bind the reference clock to the real-time clock of the controller. And this one's fairly easy because the reference clock is just downstream of the master. So the master calculates the difference in the time and then writes this time with the propagation delay to the system time offset of the reference clock only. Leslie, I'm trying to advance the slide here. There we go. Okay. So that time is sent to the reference clock. So this sets the time of the reference clock to the real-time clock of the controller, whether it's a PC or PLC. Now we have to set each slave clock to the reference clock, because each slave clock, and this can be a different value for each one because the power-up time of each slave device can be different. A drive has a different power-up time than a very simple I/O module, for instance. So the value can be all over the board. Maybe a user only powered down a certain part of the machine. The rest of the machine has been up and running for a year, for instance. So we have to get all of these individual slave clocks set to the same time as the reference clock, and this is called offset compensation. So the master calculates the offset between the reference clock and each of the individual local clocks by reading the local clock value of each slave device. And then with respect to propagation delay, distributes this time in order to get all of the local times to the exact same time, which matches the reference clock. So to each one of those devices, it writes a different value, which now brings all of our slave clocks to the exact same time. And keep in mind, the master handles all this behind the scenes, so you typically don't have to do anything here. So now all of them are set to the same time, but they can drift because each oscillator could be running at a slightly different speed. So for this, we do drift compensation, and this is where that read multiple write command comes in. So this allows, with one single frame, to read in the system time of the reference clock and then distribute it to all the slave clocks using the same path that our original propagation delay measurement used. So using the same propagation delay and distributing the time, we now can keep all of the clocks synchronized with a simple, very, very simple equation down here at the bottom. It becomes a Boolean. When the received time comes in, the slave device looks at the received time and compares it with regards to propagation delay, what time it thinks it should have. So if the delta t between what it thinks it is, what it thinks the time is, and what was distributed from the reference clock is a positive number, then it needs to decelerate its clock. In other words, it needs to count each tick of its oscillator as less time. If it's less than 0 or negative number, it needs to speed up slightly. So it needs to count each tick as more time. So with this phase lock loop, there's no jumps in time. It's only a drift in how much we're counting each oscillator tick. So excuse the poor graphic here, and hopefully it'll show up okay, but a frame comes through and grabs the reference time, and that time is sent through the entire system, and now the responsibility for checking whether or not the slave device is in time is actually up to the slave device itself. And by issuing this command more frequently, we can keep the time tighter, or the synchronization across the network tighter. So it can become a trade-off between bandwidth and your performance that you need, although the performance is pretty doggone good, as you'll see coming up. So this drift compensation really is the key to keeping everything within the same time. And because this read multiple write instruction distributes the reference clock time each time the instruction is called, and because the propagation delay of the system didn't change, so it's a known quantity, therefore we actually don't have to have jitter-free frames to have a jitter-free system. So the network itself can be perfectly synchronized while having a PLC or a PC that has a standard Ethernet port on it and have a little bit of jitter in the frames. So we don't need, therefore, a special card which has its own clock on it to send out 100% jitter-free frames, even for the most tightly synchronized applications. For instance, using a standard PC and an EtherCAT master stack with distributed clocks, 300 and some odd nodes of digital outputs, and looking at the interrupt on node 1 compared to node 300, we get a jitter of plus or minus 20 nanoseconds. And this is on a lab bench, of course, but in the field you'll typically see less than 100 nanoseconds. So the only thing that really can affect this is temperature transients on the wire, or large changes in the network topology, which, keep in mind, you can quickly recalculate the propagation delay and then keep your clocks going in synchronous mode. So if you have a need for synchronizing multiple networks, you can do this via a boundary clock, where one of the clocks is the reference clock for another network, and just have multiple networks connected through boundary clocks from different masters. And you can also synchronize to an external source, such as a IEEE 1588 source, or a GPS pulse, or any other external source through a similar boundary clock. So this would be a device that you would purchase from a vendor of EtherCAT devices that's intended to be a boundary clock. So some features of the EtherCAT distributed clocks. You've seen how the synchronization between the EtherCAT slaves and the master works. But now, what do we do with it? So I'm going to take you through some sync signal examples, precise time stamping, and then IRQ signals and how those are applied. So if we want to take an action or command an output based on a specified time. Built into this distributed clock unit are typically two pins called sync 0 and sync 1. And sending a command with a time value enables a compare unit within the EtherCAT slave controller chip in hardware that when those two values are equal, you can command these outputs to execute. So this is very handy for a low-cost digital output module that has time synchronization on it without a microcontroller. It can also be set up to be cyclic or single shot with or without an acknowledge. Also, so the converse of what we just saw, reaction to an external signal through the latch 0 and latch 1 pins. If the EtherCAT slave controller device is configured accordingly, it can store the current local time when it sees an edge on the latch 0 or latch 1 pin. And these can be configured for rising or falling or both, and single event or continuous latch. So these can be implemented for a low-cost digital input module, which would take the place of a high-dollar device with a microcontroller embedded in it. Or you can also use this, as you've seen, for latching the time of EtherCAT frames, etc. So some pretty low-tech examples, but interesting examples of using the latch and sync. So the red pattern here is what we're actually measuring in the field. This is with digital inputs, digital outputs, and a classical control system where you are examining the state of bits on each scan. So here we have an event that's occurring between the scans of our system. In an event such as this, in a classical control system, you're just going to miss that event. So if you have a very simple logic where you're just echoing the output to match the input, you will have missed this entire transition because it occurred between the scans. When we do catch an event, such as here, when we have a scan and we see that this was high, we don't know how far in advance it transitioned and what the duration of the pulse was. So if it went high, went low again on the next scan, we just have to make an assumption that it was the length of our scan rate. Similarly for the next waveform, which transitioned just before the scan came through and then transitioned sometime afterward. So this is classical controls because we don't know how long things occurred, we don't know when things happened. With a timestamp input, we can grab those times, these times here that things actually occurred. So in this example, we're using the rising edge, but you can use both the rising and falling, or just the falling. And we can command a output with timestamp to execute a command with a fixed constant value after we saw that input. So this behavior here, this reaction to the input, could be just a fixed constant, or it could be a constant based on, for instance, the conveyor speed of your system, where you're reacting to it and you're calculating how far down your cutter or your rejection device is for your bad product. So with classical controls, we don't have the constant reaction. And plus we can miss events that occur in between. And this is just digital. So for a device that might have a microcontroller embedded on it, such as a drive or a terminal that is set up for doing data acquisition, we have an IRQ pin that we can route the sync signals through. This allows us to interrupt the microcontroller in order to do synchronous things, do sampling, high precision sampling of input parameters, or execute doing outputs. So examples of this would include interfacing to a microcontroller for a power drive or electronic shaft encoder, or doing data acquisition for condition monitoring or low-level oscilloscopes on the same system that you're using your EtherCAT as a control platform. So for instance, oversampling on a an analog input or an analog output will allow you to either capture waveforms using standard I/O or create waveforms using analog outputs. So in other words, doing function generation with analog output devices. So you have a base cycle time, but you have subordinated clock cycles within that where you're either capturing or setting output values. Now, the only real important thing from the master perspective is that the data that we're going to execute has to be received, so the frame has to be received and pushed through all the slave devices, even the very last one, before the interrupt occurs. So the master application actually has to measure its own frame length that it's going to send out. Also would be handy to measure its jitter, so it'll probably give a user shift, which is designated by this U. And then the frame delay, in other words, how long does it take, but based on how long the frame is, how long does it take the frame to get through all the slave devices before our sync signal executes in each slave device, and importantly the last device in the field. And then at the slave device, the user can actually configure also a sync shift before the sync signal will execute, just in case there's some other delay in the slave device, or if you have some type of physical layer transition that's not calculated by the propagation delay measurement. So we can manually shift the sync signal. So all this comes down to is that the master just needs to make sure how far ahead to send the frame out before the last slave in the network needs the data for the distributed clock base. So a summary of what we've just gone through very quickly here is that in EtherCAT we can have a tight synchronization between the EtherCAT slaves and the master without the use of a special field bus master card for EtherCAT. And these DC features of devices are enabled by both the unique communication principles of EtherCAT and built-in features of the EtherCAT slave controller chips. And some of these behaviors built into the devices are synchronous reading of input signals across the network in different devices, precise timestamping of input signals, latch signals, for instance, and synchronous generation of interrupts to local microprocessors, the IRQ signals. And these are determined really by the vendor of the devices that you're buying these from as a user. So your drive manufacturer, your I/O manufacturer, but these you can look for when you're shopping for EtherCAT slave devices. So for more information about EtherCAT, about how distributed clocks works, or any other technical detail about EtherCAT, feel free to visit us at ethercat.org, and contact information for both our headquarters and my local office are given on this slide. So that concludes my presentation portion of this webinar.
Thank you very much, Joey. We appreciate all the information. Just a reminder to everyone, if you would like to submit your questions, feel free to do so. We are going to begin the question and answer portion of this webinar. And one of the first questions that has come in, Joey, is the frame size generally a fixed length from the master, or is it a flexible size based on the slave devices?
The frame size depends on the needs of that scan rate, and also or if you're doing any asynchronous communication through a service channel. So the frame size is dynamic for sure, depending on just what's been configured. So there, as long as we meet the requirements of 802.3, so minimum frame size of 84 bytes and a maximum frame size of 1500 and I think it's 44, so 1500 bytes of data. It can be anywhere in between.
Okay. Another question that has come in is the ring topology was not shown on this presentation, but how does this topology impact the DC function, especially if a node is dynamically removed or reinserted?
Actually, that's a very good question. So the ring topology previously has been a little bit of a problem. You still use distributed clocks, but once your topology changes, then of course you have just changed the propagation delay throughout the network. So the in the works right now is methods for having both a backup reference clock for the, I guess it would be called the portion that's remaining if you have a break in the middle somewhere. But at any point you can still recalculate the individual propagation delays between the two halves that are left over and quickly resynchronize within a matter of fractions of a second. Very good question.
Okay, this one came in, I hope I'm getting this one right. How to measure performance of synchronization?
Yeah, so that's also a very good question. So has been a push by some of the IP-based protocols to measure frame jitter and consider that a surrogate for your system performance. But that really, even with those systems, that really doesn't tell you how good you are down to the wire. So in other words, the signal out and the signal in. With EtherCAT, most slave developers are measuring the actual pins that are being used in the network. So as a developer, you have access to the interrupt pins, and you can put them on a large network and put them on an oscilloscope and measure your jitter. As a device purchaser, so as a device user, you can do a similar thing with, for instance, digital output modules. You can create a network with your digital output modules, and as long as they have a good filter time, so typically these are I/O is more tailored for EtherCAT these days, so there's I/O out there that has 1 microsecond filter times, digital modules. You can throw those on an oscilloscope and also check out the performance of EtherCAT. But it's not the frame jitter. That's the important thing with EtherCAT. We allow the frames, we expect the frames to jitter coming from a standard PC, a standard controller with a regular Ethernet port on it.
Okay, can you describe the service channel a bit more?
Yeah, it goes beyond this particular presentation on distributed clocks, but the service channel is the way we handle asynchronous communication. So either configuring of input and outputs on a device or moving standard Ethernet frames through EtherCAT. So if we want to service a Modbus TCP device or a web browser on a device, then we can use any leftover bandwidth to tunnel those protocols inside the cyclic EtherCAT frames. So it's called a mailbox in the EtherCAT world, and you can go to the ethercat.org website, and there's a technology overview which talks about that in probably more detail than I could fit in the rest of our Q&A session here. But the typical implementation of EtherCAT, you have leftover bandwidth. So we can use it for this acyclic communication while keeping our process data frames very regular, instead of having to set aside a big chunk of time just in case we have acyclic data.
Okay. This looks like a follow-on question to the topology one. So if the topology changes, how often does the master need to resend to synchronize? Or how often will the master resend to synchronize?
It really depends on the tightness that you're trying to keep the network, but the master knows when the topology changes at any point, so the master can detect those topology changes. You don't have to wait for things to go out of sync before you can execute a recalculate of propagation delay and a resync of the clocks. And then the master can be configured to send all of those configuration propagation delay frames in between your process data frames. So it doesn't have to sacrifice process data for servicing of the distributed clocks of the network. Hope that answers that.
Okay. Another question here is, what makes EtherCAT's version of the DC more precise than the IEEE sync standard?
Well, I think the specification for IEEE, there's several versions. So the typically implemented IEEE 1588 in industrial communications, at least in industrial Ethernet, does not go down to the nanosecond level. It's tied more to what's going to be serving up the real-time clock. Whereas with EtherCAT, some of the benefits are that this is already built into these chips, which can cost as low as $5 in the slave devices. And so there is no extra hardware to add, such as 1588 support on the slave devices, which requires extra hardware. And the the distributed clocks take advantage of the way EtherCAT uses the frames instead of having individually routed frames within the network. So internally, the user really shouldn't concern themselves whether the synchronization is with IEEE 1588 or with distributed clocks, but in the EtherCAT world, it's going to be DCs. The performance is higher, but also because it's integrated into the slave chip, you get the direct inputs and outputs to the wire directly from the chip and directly from the commanded time or latch time. So you don't have another layer of drivers to go through from a 1588 support chip to whatever device you're controlling. So it's as a overall system, it's much tighter.
Okay. And someone has asked whether or not you can use Wireshark to capture the EtherCAT packets? Certainly
can. The parser for EtherCAT has been in Wireshark now for 4 or 5 years, and it is actually a dynamite tool. It's free, and all of the commands you can interrogate and see everything that's going on in EtherCAT with Wireshark. So it's really the only sniffer tool you need. You don't need a high-cost canalizer or any other similar tool with EtherCAT.
Okay. And is the DC block optional in the ESCIP, or does it come standard by default, or does it come by default?
It's a feature that can be turned on or off. So if the question referenced IP, so I'm assuming that that's talking about FPGA implementation. So it's a part of the configuration that can be turned on or off. it's another one of those balancing things. So if you need it, obviously you need it, but you can turn it off to save power and make a use less pins, for instance, and have a cheaper device. So you typically don't have to do timestamping with a push button from an operator, for instance. So no need to use distributed clocks for generic I/O, but for time critical or time sensitive, or for getting rid of dedicated sensors on the network and just go into dumber photo eyes and other types of commodity sensors, then DC enabled devices make a lot of sense.
Okay, this is a follow-up to the Wireshark question. It's this questioner's understanding that you needed a special device to receive the high-speed timestamping of packets. Is this no longer the case?
You can examine EtherCAT frames with a standard switch, a standard unmanaged switch. Just place it into the network. Since the EtherCAT frames are broadcast, they'll be sent out to all ports of the switch. So your whatever computer you're using with Wireshark can be plugged in, and you can sniff them there. If you need the timestamps, then there are probes available from a couple of different vendors. Beckhoff makes one, and I believe a couple of other vendors make them, but that's only if you need the timestamp down to the nanosecond, and most users don't need that. They're really typically just looking at the commands and responses out there.
Okay, and here's another follow-up. What is the accuracy of timestamp in Wireshark?
Nanosecond.
Okay. And another one, can EtherCAT run at current full Ethernet speeds? And he's having an example of 40 gigabits per second.
Right now, EtherCAT is 100 megabit per second only. So that's in the future, as the need for faster systems continues to grow, then EtherCAT will probably migrate to those. But at this time, for automation, 100 megabit EtherCAT is much faster than gigabit Ethernet protocols, for instance. Most gigabit Ethernet protocols, if not all. So controlling hundreds of axes in the microsecond range, millisecond range is all that is required these days. So we'll be there when it's a necessity for automation, but 40 gigabit is a pretty specialized animal right now.
Is anyone routing EtherCAT?
Sounds like, is anybody routing EtherCAT through the internet? And no, they're not.
Okay. And we do have a question here. I'm not quite sure about how we would address this one, but when someone was asking is, will there be a PDF version of this presentation available? They say that there are some points, some important references that are difficult to remember. Just a reminder, you will be receiving this webcast in email in the next day or so, and it's also available on our site. Joey, I think it's kind of up to you if you want to make this available in a PDF format for people.
What was the distribution method for?
I imagine
it's just going to be the webinar?
Yeah, it'll be sent out to the people who've registered, sent out via their email.
Yeah, I'm fine distributing the contents as a PDF, or
okay,
having people download it if they wish.
Okay. And we have a follow-up question here to the routing EtherCAT. He said not routing to the internet, but routing internally into subnet domains.
You can use VLAN tagging with EtherCAT. So if you need to have individual EtherCAT networks coming from one master, you can use a VLAN switch and then specify which port the EtherCAT frame comes out of that port. Other than that, internally within an EtherCAT network, there's no routing of frames. That's what makes it so efficient and so fast.
Okay. We have time for one or two more questions. The person who asked that question says, understood, thanks.
Gotcha.
And if you wish to continue to ask questions, feel free to contact Joey at his web address or his email address. You can see it there. It's j.stubbs@ethercat.org. And if there are no further questions, I'd like to thank everybody again for attending. And one more time, this presentation will be emailed to you probably in the next day or so, and it will also be available on the Design World online website. So thank you very much, Joey. This was a very informative webinar. I think everybody got a lot out of it.
All right.
We appreciate your time. And thank you, everybody, for attending. Great questions.